Our topic in this lecture is inner product space. Inner product space. So, IPS. What happens is you have a vector space. You have a vector space V and you have a vector space V. You cross it. When you cross it, you have one element from V and other element from V, and you want to make a function which goes to f. F is the base of f. So inner product space is defined as this thing. So since you have two elements of V, so you put one element here and second element here from V cross V. This means the input and it goes to f. Okay, is said to be IP inner product, is said to be inner product, and V is said to be VF is said to be inner product space if following properties are satisfied. If following properties are satisfied. So first property is, see, for example, you have VW, and if you do WV, then it will be conjugate first. Then you have V1 plus V2 comma W. This will be V1 comma W and then V2 comma W. Then you have third property. Third property is alpha V comma W. Alpha will come out and it will become V comma W. I hope it is clear to you. Then you have fourth property, a definition. When you write a definition, then you write some laws, and laws are as it is, you have to remember them. Second is V comma V will always be positive, and V comma V can be equal to 0 if and only if V is equal to 0. If these properties are satisfied, then we say that this thing is inner product and V is inner product space. So example, this is definition. Then example is standard inner product on Rn. Standard inner product on Rn. What is this? Rn, you know, Rn is x1, x2 up to so on xn. This is Rn. This is element of Rn. You need two elements, so you take y1, y2 up to so on also. So you can represent them by V and W respectively, and these elements belong to Rn. So standard inner product says V comma W will be, what is this? This is dot product of V dot W. So you know how to do the dot product. Dot product is simply x1 y1 plus x2 y2 plus to so on xn yn. So this thing is called standard inner product, and it will satisfy these properties. Now second is standard inner product on Cn. First and second, standard inner product on Cn. So in the same as you have done this in this, same thing is in this also. Here you have element in Rn, same element, now they belong to Cn. So you say V is x1, x2 to so on xn, and W is y1, y2 up to so on yn, and here the elements belong to Cn. Now if the element belong to Cn, when you do the inner product, it will actually remain the same, but there is a simple difference that on second element you will take bar. It means that you will write summation I from 1 to n, xi as it is, yi with bar. I hope this thing is clear to you. So this is basic definition. One more thing, this is norm of a vector. Norm of a vector is V norm, and V norm is actually V comma V. Norm of vector, length of vector you can say. Norm is also called length of vector. Length of vector. So this is the one. This is one thing. One more thing is orthogonal vectors. Orthogonal vectors. You say that v1 comma v2 are said to be orthogonal if v comma w in a product, if v comma w in a product is c. Okay. Now one more thing. This is Pythagoras theorem. Pythagoras theorem. Pythagoras theorem is simply v1 plus v2 norm square is equal to v1 norm square plus v2 norm square. So you have this thing. You need one lemma here. What is this? This is like if you have okay, no need of lemma, we will do directly because it is just a 2 marks question. Proof is you have this thing v1 plus v2 norm square. This means this thing. So this is v1 plus v2 comma v1 plus v2 and you have this property. This property says that things can get separated. When you separate them, it becomes v1 comma v1 plus v2. Then you have v2 comma v1 plus v2. I hope this is clear to you. Then now we have property that this thing, if plus is on the first element, then the elements will get separated. But if the elements are on second side, on second place, and if they are in addition, then we can distribute them or not. This is actually the lemma. So we write just 2 steps here, that v comma for example w plus vw. Okay, v1 comma v1 plus v2 will be equal to v1 plus v2 comma v1 bar will be equal to v1 plus will be equal to v1 comma v1 and then v2 comma v1 whole bar, and bar will get separated, so it will become v1 bar and then v2 v1 bar, and this thing will become v1 v1 and this thing will become v1 v2. I hope this thing is clear to you. You can reverse the order. When you will reverse the order, you will have to apply bar, and you can remove the bar. When you will remove the bar, you will have to reverse the order again. So what I'm trying to say is this thing will become v1 comma v1, then this thing is v1 comma v2. This is first, then second will be, this is second, this will become v2 comma v1 plus v2 comma v2. Just distribution of elements. So you have 4 things. Now Pythagoras says v1 square plus v1, this thing is equal to this when statement is when v1 and v2 are orthogonal. So given v1 comma v2 are orthogonal. If they are orthogonal, then the inner product is 0. So you have v1 comma v1 and then you have v2 comma v2. All other things are 0. So it becomes v1 mod square, norm square, sorry, and v2 norm square. I hope this thing is clear to you. This is very easy. Next is orthogonal set. Orthogonal set. So what is orthogonal set? You have a set. First of all, you have a let capital VF VIPs in a product space, and then you say that there is a set V1, V2 up to Vn, V set of elements of VF non-zero, we set of non-zero elements of VF, then then this set this set is said to be orthogonal. Then this set is said to be orthogonal if what happens is V1 is orthogonal to V2, V3 up to so on, all elements. V2 is orthogonal to every element, V3 is orthogonal to every element is orthogonal to the rest of the elements. Okay, if Vi comma Vj, this thing becomes equal to 0 for all I not equal to j. See, if you have I comma I, if you have I is equal to j, then it becomes the norm, and norm will be equal to 0 only when the element is 0 itself. But element that we are taking is non-zero. So you say that you have, first of all, you have a vector space and you have a field. This is vector space, this is field. You have some elements in this. These elements are all non-zero. The non-zero elements are said to be, see, first of all, you have orthogonal elements. Two elements are said to be orthogonal if they are orthogonal with respect to each other. Then you have three elements are said to be orthogonal set, they will make a set. So you say this is a set of three elements, and v1 v2 v3, v1 is orthogonal to v2 and v3, v2 is orthogonal to v1 and v3, v3 is orthogonal to v1 and v2. So this is the thing. Second is, okay, second is orthonormal set. Orthonormal set. Orthonormal set. You say that you have a vector space and base is f. This is vector space. You have base and you have some elements. Okay. Now things remain the same. This is IPS, set of non-zero elements, so and so. First line remains the same. Fine. Second is, then the set to be orthonormal. Now you have two things, ortho plus normal. Ortho means they are perpendicular with respect to each other, and normal is, see, what is the meaning of normal? A unit vector. Unit vector means whose norm is equal to 1 is said to be a normal vector. Okay, so you have v1, you have vi comma vj. Okay, you have vi comma vj. If I is not equal to j, this means v1 v2 v1 v3 v2 v5 v5 v10, something like this. So the elements are orthogonal, so it will be 0. Then you have I is equal to j. When you have I is equal to j, you can understand that it will be v1 v1 v2 v2 v3 v3. So you know that this thing is norm, actually norm square rather, and you want this set to be a normal set also, and a vector is said to be normal if its length is 1. This means that if I is equal to j, it will be vi norm square, but since we want the vector to be normal, therefore this norm will be equal to 1. So you say this is, sorry, you say this thing will be equal to 1. So a set is said to be orthonormal set. In an IPS, you consider a set of non-zero elements. Then those non-zero elements are orthogonal with respect to each other, and to himself the vector is a normal vector. Then the set is said to be orthonormal set. I hope this thing is clear to everyone. Second is conversion of orthogonal set to orthonormal set. Conversion, this is a very simple thing. Orthogonal set says that this thing, the norm of, sorry, the inner product of two different vectors will be equal to 0, and orthonormal says inner product of two different elements is 0 and that of same elements should be equal to 1. Now you have, for example, this is standard notation. You have this v1 v2 up to so on. This vector is orthogonal vector, is orthogonal set, is orthogonal set. What you do is you say we write a new set. Which set? We form a new set on the same thing. We form a new set. We form a new set v1 upon v1 norm, v2 upon v2 norm, up to so on vn upon vn norm. Say this is u1 u2 up to so on u1. Just a standard notation. In many books it is written e1 e2 up to so on. Doesn't matter at all. Okay. So you have u1 u2 up to so on. This is new set that you have formed. Say means suppose you want to write it w1 w2 up to so on, you can write, doesn't matter at all. Now we want to check that the set that we have made is orthonormal. Okay, so you do ui comma uj. When you do ui comma uj, it will be vi by vi norm comma vj by vj norm. In this way, you see this thing and this thing, they will be out. It will be vi norm and then vj norm 1 upon, and then it will be vi comma vj. Now we ask this thing, that what is this? And you say that this set is orthogonal. If I is not equal to j, then this thing will surely be equal to 0. This inner product will be equal to 0, and if I is equal to j, then this thing will be 1 upon vi norm and vi norm again. I is equal to j. This thing is vi and vi, vi and vi. So you see, what is this? Norm square. What is this? Norm square. So it will become 0 and 1. I not equal to j and I is equal to j. I hope this thing is clear to everyone. This is very easy. Next is a theorem. Theorem says that an orthogonal set is always linearly independent. Is always linearly independent. So corollary will be an orthonormal set is always linearly independent. I hope this thing is very clear to you. Nothing in this. See, there is no difference between orthogonal and orthonormal. Main thing is they are orthogonal. Normal means their norm is 1. Okay, nothing special in this. So we want to check that, we want to prove that orthogonal set is always linearly independent. So what is the definition of linear independence? If you have linear combination is equal to 0, then the scalars should be equal to 0. So you say that let v1 v2 up to so on vn be a orthogonal set in IPS VF, in a product space VF. Fine, orthogonal set. Given that this is an orthogonal set. Fine. Then you say let alpha 1 v1, alpha 2 v2 up to so on, alpha n vn is equal to 0 for some alpha 1, alpha 2 up to so on, alpha n, they all belong to F. How we prove linear independence? We take linear combination equal to 0, then we prove that all scalars are equal to 0. If all scalars are equal to 0, then the vectors are automatically linearly independent, hence the set is linearly independent. So we want to prove that if somehow after writing 3, 4, 5 10, 20, 100 steps. If I can say that alpha 1 is equal to alpha 2 up to so on is equal to alpha n, all are 0, then by definition v1, v2 up to so on vn is linearly independent. Hence orthogonal set is linearly independent. Somehow if I can prove that alpha 1, alpha 2, so on alpha n, all scalars are equal to 0. We want to prove this. Now what happens is, very simple thing, you take alpha 1 v1, alpha 2 v2, so on alpha n vn, comma vi, this thing equal to v comma 0 comma va. So you take inner product with respect to vi. You can write vj also, up to you. Okay, for convenience I write, for example, I write vj. Now what will happen? This thing will distribute itself. It will become alpha 1 v1 comma vj, then alpha 2 v2 comma vj. I hope this thing is clear to you. Up to so on alpha j vj comma vj, up to so on alpha n vn comma vj, and right hand side is inner product with respect to 0, so it will be equal to 0. You know this. Now the set is orthogonal. If the set is orthogonal and you take two different elements, this will give 0. This will be 0. All things will be 0. This thing will not be 0. vj, two elements, both are same. It will be norm. Norm is not 0. Element is, since the element is non-zero. Why element is non-zero? Because orthogonal set is given. The word is given orthogonal set, and when you see the definition of orthogonal set, it says that the element should consist, the set should consist of non-zero elements only. So this means that alpha 1 into 0, alpha 2 into 0, up to so on, all things are 0, alpha j into norm. Fine. Then all other elements are again 0. Now what happens is this thing says, in simple sense, this says alpha j vj norm square is equal to 0, and the norm is not 0. If the norm is not 0, this means alpha j is equal to 0. Now when you take inner product with respect to j, you can take j anything, 1 2 3. For example, in first go I take v1, I take j is equal to 1, it will be 1 1 here, alpha 1 will remain, all other things will become 0. It will give alpha 1 is equal to 0. Then I take v2. If I take v2, only v2 will remain, all other things will be 0. It will give alpha 2 is equal to 0. It will then again 3 4 5 up to so on n. So you say implies alpha j is equal to 0 for all I from 1 to n. Sorry, for all j from 1 to n. Doesn't matter if you take I, then it will be I in all terms. If it is j, then it will be j in all terms. So you say all scalars are 0. If all scalars are 0, then you say the definition is linear combination has been put equal to 0 and all scalars become 0. Element will become linearly independent, hence set will become linearly independent, but the set is orthogonal set, so you say orthogonal set is always linearly independent. I hope this thing is clear to you.